Hi everyone, I'm Hossein and welcome to episode 7 of the Grasshopper From Zero series. In this lesson, we're going to explore one of the most interesting and practical topics in computational design, trusses. We'll cover both 2D trusses and space frames, and you'll learn how to generate them parametrically in Grasshopper. As always, we're not just going to look at the final result. We'll build the algorithm together from scratch, step by step, understand the logic behind it, and practice each part along the way. You'll also get familiar with several useful Grasshopper components that you'll find yourself using in many other projects. Before we jump into Grasshopper and start building the algorithm, I'd like to spend a few minutes talking about trusses themselves, what they are, why they were developed, how they transfer loads, and what makes 2D trusses different from space frames. Once we understand these fundamental concepts, writing the algorithm becomes much more intuitive. So let's begin with a quick introduction to trusses, and then we'll move on to the practical part of the tutorial. Let's first understand what a truss actually is. Simply put, a truss is a structural system made of straight members connected together. These members are typically arranged into triangles, allowing loads to be transferred efficiently to the supports. The reason triangles are used is simple. They're one of the most stable geometric shapes. Unlike other polygons, a triangle resists deformation without changing the length of its sides, making it ideal for structural systems. So, why do we use trusses? Their biggest advantage is efficiency. Trusses can span large distances while using a relatively small amount of material, yet still provide excellent structural strength. That's why they're widely used in warehouses, sports halls, bridges, long-span roofs, exhibition structures, and many modern architectural projects. In general, trusses can be divided into two main categories: 2D trusses and 3D trusses, also known as space frames. In a 2D truss, all the members lie on a single plane, and the structure carries loads within that plane. A space frame, on the other hand, extends into 3 dimensions, forming a spatial network that provides greater rigidity and makes it ideal for covering much larger spans. In this tutorial, we'll explore both types. We'll start by building a 2D truss algorithm from scratch in Grasshopper, learning the logic behind it step by step. Then we'll expand the same approach to create a fully parametric space frame. By the end of this video, you won't just have a finished model, you'll have a flexible algorithm that you can easily modify, customize, and adapt to your own architectural projects. Before we move into Grasshopper, let's take a quick look at the main parts of a truss. Once you understand this basic structure, building the algorithm becomes much more straightforward. First, the points where the members meet are called nodes. Every connection in the truss happens at these points. The lines connecting the nodes are called members. These members carry and transfer the loads throughout the structure. The distance between 2 adjacent nodes is called a bay. As you add more bays, the truss simply becomes longer. Now, if we look at the overall shape of the truss, the horizontal members along the top are called the top chord, while those along the bottom are the bottom chord. Together, they form the primary framework of the truss. Between these 2 chords, we have 2 types of members. Vertical members run straight up and down, while diagonal members connect the chords at an angle, dividing the structure into stable triangles and giving the truss its strength. So, if I had to describe a truss in one sentence, I'd say this. A truss is simply a collection of nodes connected by members, where a repeating pattern creates a structure capable of spanning different distances. And that's exactly the same logic we're about to recreate in Grasshopper. Now let's move on to the practical part and build a 2D truss from scratch in Grasshopper. I'll start by creating the bottom row of nodes. To do that, I'll use the construct point component. Instead of entering each coordinate manually, I'll generate the x values parametrically using a series component. I'll connect the output of series to the x input of construct point. Now let's configure the series. I'll set s, the starting value, to 0. I'll set n, which controls the step size, to 5. Finally, I'll set c, the number of values, to 11. This value doesn't have to stay fixed. We'll make it fully parametric later. At this point, we have the bottom row of nodes. Next, I'll create the top row by copying this set of points, but with one important difference. The top row should contain 1 fewer point than the bottom row. To do that, I'll use the subtract component. I'll connect the value 11 to input A, connect 1 to input B, and then feed the result into the C input of the second series component. Finally, I'll set the Z coordinate of the second construct point to 5, lifting the second row upward and creating the top chord of the truss. Now, all the nodes are in place. The next step is to connect these points in a zigzag pattern. We want one point from the bottom row, then one from the top, then the next point from the bottom, followed by the next point from the top, and so on until we reach the end. To achieve this, we'll use the weave component. The purpose of weave is to merge multiple lists according to a specified pattern. I'll connect the bottom row of points to input 0 and the top row to input 1. Now we need to define the pattern. I'll create a panel and enter the following values on separate lines: true, false, true, false. Then I'll right-click the panel, enable multi-line data, and connect its output to the P input of the weave component. As you can see, the points are now ordered exactly the way we need. Next, I'll connect these points using a polyline component. You could also use interpolate curve here if you prefer. I'll simply swap inputs 0 and 1 on the weave component, so the path starts from the side that produces the truss layout I want. Now I'll create 2 additional polyline components to connect the bottom row and the top row separately. This gives us the bottom chord and the top chord, completing the primary framework of the truss. At this stage, the truss structure is almost finished. To give it a more realistic appearance, I'll send all 3 polylines into a pipe component. For the diagonal members, I'll use a radius of 0.1. For the top and bottom chords, I'll use 0.2, making the primary structural members slightly thicker and visually easier to distinguish. As you can see, we now have a 2-dimensional truss with tubular members. Finally, let's make the model a little more flexible. I'll pass the top row of points through a move component and control the movement along the x-axis with a slider. Then I'll replace the original top points with the moved points in both the weave component and the top polyline. Now, by adjusting a single slider, we can shift the top nodes and change the overall shape of the truss without modifying the algorithm itself. And that's it. Our first parametric truss is complete. From this point on, changing parameters such as the number of bays, the spacing between nodes, the truss height, or the horizontal offset of the top nodes will automatically update the entire structure. If you found this video helpful so far, I'd really appreciate it if you could support it by clicking the like button and giving it a hype. These 2 simple actions make a huge difference. They help the video reach more people and support the growth of the channel. Every like, every hype, and every comment motivates me to keep creating more tutorials like this. I'd also love to hear your thoughts. If you have any questions, suggestions, or feedback, feel free to leave a comment below. I do my best to read every comment and answer as many questions as I can. And if you haven't subscribed yet, make sure to subscribe and turn on notification so you don't miss the upcoming videos in this series. Also, I recently launched a Telegram channel. You'll find the link in the video description. My goal is to stay more connected with you and share extra resources, files, tips, and behind-the-scenes content that doesn't always fit into a YouTube video. All right, let's get back to the tutorial. Now let's move on to the more exciting part of this tutorial, building a 3D truss, or more commonly, a space frame. The overall idea is very similar to what we did in the previous exercise. The difference is that instead of working along a single line, we'll start with a 2-dimensional grid and then extend it into the 3rd dimension. To begin, we'll create a base surface. Instead of using a predefined rectangle component, I'll build it from scratch, so the entire model remains fully parametric. That way, changing just a few values later will reshape the entire structure. I'll start with 4 construct point components and define the corner points like this. Point 1 is located at x hit 0, y bit 0, z hit 0. Point 2 at x bit 0, y bit 10, z hit 0. Point 3 at x bar 10, y bar 10, z hit 0. And point 4 at x bar 10, y 0, z 0. These 4 points define a rectangular surface. And since everything is controlled by numeric values, we can easily change its size or proportions at any time. Next, I'll use the 4-point surface component and connect the 4 corner points to create the surface. Now we have a fully parametric base surface. The next step is to divide it into a grid. I'll use divide domain 2, connect the surface to its I input, and leave the U and V divisions at their default values of 10 by 10. Then I'll use Isotrim, connecting the surface to S and the output of divide domain 2 to D. As you can see, the surface is now divided into a grid of smaller panels. To access each panel individually, I'll connect the output of Isotrim to deconstruct BREP. Now we arrive at one of the most important parts of the algorithm. To build a space frame, we first need to know which direction each panel is facing. This is where the normal vector comes in. Simply put, a normal vector is a vector that is perpendicular to a surface. It tells us the orientation of that surface. If we want to extend a new structural member upward from each panel, the normal vector gives us exactly the direction we need. To calculate this information, I'll use evaluate surface. I'll connect the face output from deconstruct BREP to the S input. To specify the evaluation location on each panel, I'll connect an MD slider to the UV input. Before continuing, I'll right-click the S input and enable reparameterize. This normalizes the UV coordinates to a range between 0 and 1, ensuring that the MD slider behaves consistently across every panel. Now we have both the center point of each panel and its corresponding normal vector. Next, I want to draw a line from the center of each panel along its normal vector. For that, I'll use line SDL. The center point goes into P, the normal vector into D, and I'll set the line length to 1 for now. This value represents the height of our space frame and can easily be adjusted later. Now our reference lines are ready. The next step is to connect the 4 corners of each panel to the end of its corresponding line. First, I'll use endpoints to extract the start and end of every line. Then I'll use the line component to connect the endpoint, E, to the 4 vertices of each panel obtained from the vertices output of deconstruct BREP. This creates the diagonal members for every module of the space frame. Now we only need to create the upper grid. I'll start by sending all the line endpoints into a point component and applying flatten to the output. However, there's a problem. All the points are now stored in a single list, and their order isn't suitable for drawing the horizontal and vertical members. To reorganize them, I'll use partition list. I'll connect the point list to L and set the size to 10, since our grid contains 10 subdivisions in each direction. Then I'll connect the output directly to a polyline component to generate the members in one direction. Next, I'll pass the same data through flip matrix and connect it to another polyline to generate the members in the perpendicular direction. At this point, the structural framework of the space frame is essentially complete. Now we just need to give the members some thickness. This part is exactly the same as in the 2D truss example. I'll connect all the lines to the pipe component and assign the desired radius for each group of members. Since we covered the pipe component in the previous exercise, I won't go into the details again here. As you can see, the structure now has a much more realistic appearance. At this stage, we have a fully parametric space frame. If we change the coordinates of the 4 corner points, the entire structure updates automatically. We can also control the grid resolution, the height of the structure, and the thickness of the members, allowing us to generate a wide variety of different forms. Finally, I'd like to visualize the structural nodes as well. I'll combine the corner points from deconstruct BREP with the endpoints of the vertical lines, then connect all of them to a sphere component and assign an appropriate radius. This displays every node as a sphere, giving the model a cleaner and more complete structural representation. And that's it. We've built our first fully parametric space frame, a flexible foundation that you can easily extend, customize, and develop into much more sophisticated structures for real architectural projects. And that's a wrap for this tutorial. In this lesson, we learned how to build both a 2D truss and a parametric space frame from scratch in Grasshopper. More importantly, I tried to explain the reasoning behind each step. So instead of simply memorizing an algorithm, you'll understand the logic and be able to create your own variations. I highly encourage you to rebuild both examples from scratch after watching this video. Try changing the number of bays, the dimensions, and the different parameters to see how the structure responds. That's one of the best ways to learn Grasshopper and become comfortable with parametric thinking. If you found this tutorial helpful, I'd really appreciate it if you subscribe to the channel. And if you have any questions, suggestions, or ideas for future videos, feel free to leave them in the comments below. Thank you so much for watching and for staying with me until the end. I hope you enjoyed this tutorial, and I'll see you in the next one.